participants, and welcome to you all to this second session of the third day of the program. Today's speaker, in fact, the speaker of this session is Professor Paramartha Dutta. He is working as a professor in the Department of Computer and System Sciences of Viswa-Bharati University, West Bengal. He did his bachelor's and master's in statistics from ISI Kolkata in 1988 and 1990 respectively. He has completed Masters in Computer Science in 1993 from the same institute. He received his PhD in Engineering from Bengal University and Science University, Shibpur in 2005. He is the recipient of Excellence in Science and Technology Award 2018 conferred by the Indian Science Congress Association, Government of India, and INSA Teacher Award 2019 conferred by the Indian National Science Academy, Government of India. Professor Dutta has several years of teaching and research experience. His research interest includes quantum cellular automata, cloud computing, soft computing, image processing, meta-heuristic techniques, etc. He has co-authored 8 authored books, 13 edited books, and more than 300 reputed journal and conferences. In addition, he is co-inventor of 17 published patents. A handsome number of scholars have completed their thesis, that is from master's and PhD, under his vibrant research capacity. I have the opportunity also to work under him as supervisor during my PhD. Professor Dutta is also a member of Scientific Committee and Editorial Review Board on Engineering and Applied Sciences of World Academy of Science, Engineering and Technology. Professor Dutta is a Life Fellow of Institute of Electronics and Telecommunication Engineering, Life Fellow of Optical Society of India, Senior Member of Machinery, Senior Member of IEEE Computer Society, with an endless list in his credit. He has been nominated by MHRD, Government of India, as the member expert of the selection committee for award of Commonwealth Scholarship offered by the Government of United Kingdom in 2010, and member chairman nominated by UGC of the review committee of the Special Assistance Program in the Department of Computer Science and Automation, Indian Institute of Science, Bangalore in 2011. This is just a brief view of the of Professor Paramartha Dutta. I hope this is enough with this short span of time. With this brief introduction, I welcome you to this platform, and I take this privilege to hand over the session to you. Sir, please.
So thank you, Janto, for your. So at the outset, I want to avail this opportunity to express my gratitude to IT Department of Tripura University for allowing me to ventilate some of my works, recent works, better to say, in this AICT program, ATAL program. I hope that it will be an enjoyable one for all of us. So let me share. So incidentally, today's topic is 2.1 electron quantum cellular automata circuits. In fact, quantum cellular automata happens to be one very formidable component of quantum machine or quantum platform. Very much very formidable alternative to quantum computers days ahead. It has got its limitations as well as strengths, which in course of my discussion I shall try to elaborate. Incidentally, today's topic is a 2.1 electron variant of quantum cellular automata, primarily used for design of circuits, digital circuits. But it is post 4.2 electron quantum dot cellular automata, which commonly is used in QCA. QCA is a brief, abbreviation of quantum dot cellular automata. The 4.2 electron QCA is otherwise comparatively a popular one by now, and 2.1 electron variant of this is post 4.2 electron version, which we are going to discuss now. In fact, this particular topic is the research work of one of my scholars, who has already awarded her PhD, and Dr. Neeli Ghosh is right now an assistant professor. She has got the appointment. She is now serving as the assistant professor in regular role in North Bengal University. Recently, she has joined. It is basically her research work or PhD work, which I am going to discuss now. So, the outline of today's talk is survey and prerequisite, some issues related to energy formulation. Then there are two forms of circuit designs, non-reversible and reversible, followed by sum of discussion. However, given the time I am allowed to speak, I am not very sure whether it will be possible to cover the entire spectrum of all the topics outlined here. So let me start, and given the time, whenever or as far as possible, I shall try, and I'm going to stop there where time becomes impermissible. Okay, so regarding the survey and prerequisite, we have to understand how exactly, or better to say, what is the genesis of quantum dot cellular automata as a technology, alternative technology to classical, classical CMOS technology. How did it come and why it was at all useful and in which way? So we are going to start with survey and prerequisite. Now, the background is that Intel co-founder Gordon Moore claimed number of components in integrated circuits are doubling every 2 years. This is the empirical finding that he observed, and this observation is commonly known as or referred to as Moore's law. In literature, Moore's law means this particular observation. Professor Moore came out with. So CMOS, the prevalent technology even today, is expected to attain saturation due to this. Now, this is the bottleneck. We have to understand this. As a technological platform, otherwise very popular one, CMOS technology, even today, to be honest, it has got its saturation or limitation. Because the way the number of components in ICs are growing, at some stage or other, CMOS as a technological platform is going to show its saturation, and in fact, we want to, or rather, better to say, we need to have something more than that. That means post-CMOS mechanism or post-CMOS platform, technological platform for our purpose. And this is because of this leads to the foundation of several alternative technologies. So there are several post-CMOS technology, in some sense, they are going to come up, or they have come up to some extent. They have tried with their strengths and limitations, advantages and disadvantages. In order to understand the genesis, background genesis, it is very useful and important that we must understand the pros and cons of different technologies enlisted here. So they mostly constitute silicon on insulator, or in short, what is known as SOI, graphene, then carbon nanotubes, then quantum dot cellular automata, or QC. So, though our present topic is quantum of cellular automata, and to be specific, to be more specific, 2.1 electron variant of that for the purpose of circuit design, still, for the sake of completeness, let me discuss some issues related to other, competing technologies also, like SOI, graphene, or carbon nanotubes. So SOI, silicon on insulator, uh, is based on the concept of silicon wafers. That is indicative of that, which is nothing but a silicon insulator, silicon layered architecture. Insulator is the architecture, uh, silicon dioxide layer. So this is basically, this is commonly known in literature as bodied oxide. So basically, this is the used for the purpose of architectural aspects. So from material point of view, material science point of view, this is what exactly it is. So now, because of this, it has got certain advantages. It's got certain disadvantages also. Coming to discuss about the advantages side, delivers significant improvement in case of power and speed compared to other existing technologies. So far as power and speed are concerned, uh, SY has a very high score. Possesses a small cheap area. That means area consumption or area requirement is very limited or very short. Solving the scaling issue of CMOS technology. The CMOS as a present technology has got one bottleneck among many, which is associated to what is known as scaling issues. These scaling issues to a large extent is taken care of by SOI as an alternative post CMOS platform, technology platform. Different materials can be easily integrated as the insulator layer in the silicon wafers. Now, it's the material, with which it has to be, it may be integrated. Now, depending upon different material characteristics, there may be variable, performances, and various options have been tried, definitely with different materials, and different results have been observed. So I'm not exactly going into the details of that because exactly this is not our today's topic, but it's part of which may be proved as, or which have been proved as some favorable, favorable component of uh, silicon on insulator as a technology, alternative technology. Coming to the disadvantage side, the basic barrier in SOI manufacturing is the drastic increase in substrate cost, the cost aspect, which in turn increases the overall manufacturing cost almost up to 10% to 15%. So cost-wise, it is not that much effective. It's one strong disadvantage component of disadvantage. Then SOI possesses uh, some adverse effects also like this. So some disadvantages sides are also there, and as a result, with these pros and cons, that means with advantages as well as disadvantages, SOI is somewhat popular but not considered as a very strong alternative technology to CMOS, the post-CMOS scenario. There are other competitors as well. Coming to graphene, the other one, which is it is a solely two-dimensional substance. So in respect of substance realization, it is two-dimensional characteristically. It comprises carbon atoms arranged in a monoatomic layer as honeycomb lattice. The figure is self-indicative. Basically, um, these carbon atoms are forming lattice type of structure like this, which essentially is used as the formation of graphene. It has some unique characteristics, materially speaking, stronger than diamond. It's more conductive than copper. Very interesting combination. More flexible than rubber. So in terms of flexibility, it is more flexible than rubber. In terms of material strength, it is stronger than diamond. At the same time, it is, in terms of conductivity, it is more conductive than copper. So all the three very favorable requirements encapsulated within one. Very difficult to get an alternative. So graphene has that distinct advantage over its other competitors in respect of providing all the three together as an alternative technology. Mostly because of these, there are issues of advantages where it is the strongest and yet the thinnest material known so far. Strongest and thinnest. So both the challenges sorted out together simultaneously. It possesses some extraordinary electronic features with extraordinary crystal quality, as observed in some of the concerned literature. Its electron transfer rate is much faster compared to the conventional silicon FET. Graphene's strong interactions with photon. So, I mean, there is a photonic effect or interaction issue also, which is otherwise an advantageous part because all the materials do not support that. And stable nature in electrochemical field can prove to be beneficial to silicon-based CMOS. As per Morozov, it has poor photon electron scattering that makes it possible to attain high electron mobility even at room temperature. So it's one of the very important requirement to have all the functionalities at room temperature. We shall see that realization of different functionalities in room temperature is a big bottleneck because of adherence to room temperature cannot be compromised. And this is one of the major bottlenecks in course of our discussion. Later we shall see that in metal QCA, that technology we are going to discuss today has got some disadvantage over that aspect also. But as far as graphene is concerned, it poses as an advantage as per Morozov. Coming to disadvantage side, the absence of any band gap leading to denial of off-on mechanism in electrical conduction. So basically, when electrical conduction takes place, this off-on switching mechanism cannot be achieved. So this is one of the biggest difficulty because you cannot regulate some switching mechanism in the form of on and off. Then susceptibility to oxidized climate, presence of toxic properties. Toxicity is yet another issue of botheration because in terms of handling, it has got its toxicity aspect, tailing upon the entire effort altogether. This is another big disadvantage as far as graphene is concerned. Next comes carbon nanotube, in short CNT. Carbon nanotubes come into play to surpass the limitations of graphene. It is a cylindrically rolled up graphene sheet which has exclusive conductivity properties for both current and thermal energy. To play to surpass the limitations of graphene. So the basic drive historically speaking, was the shortcomings of graphene. How could be overcome? That was one of the cardinal factors in respect of realization or finding carbon nanotube as an alternative. It is cylindrically rolled up graphene sheet which has exclusive conductivity properties for both current and thermal energy. The advantages that carbon nanotubes offer as a technological platform. CNT has effective size and lightweight properties which make it efficient replacement of metallic wires. CNT is resistant to temperature changes, and CNT it provides high carrier mobility and ultra thin body which makes it efficient in nanoscale integration. So all the three aspects come as the as advantage in favor of carbon nanotube as an alternative technology. But it has got its disadvantages too. Cost-wise, its production cost is very high. And moreover, presence of parasitic resistance. It means not its own resistance, but resistance due to itself, but there are associated parasite called parasitic resistance. That factor is very much inseparable part of carbon nanotube technology. So this comes as one of the disadvantages. So with these advantages and disadvantages of silicon on chip, silicon on insulator SY, graphene and carbon nanotubes. Next comes today's discussion with this background. What is known as quantum dot cellular automata or QCA? QCA is yet another alternative technological platform. Now, it is our today's topic, so let us elaborate. Now, it is a new computational paradigm, needless to say. Quantum dot cellular automata refers to the merger of cellular automata and quantum information processing. So, background-wise, needs it gets the inspiration from two concepts together. One is concept of cellular automata as such, and the embedding of quantum information, the purpose of processing within cellular automata ingredient gives rise to this type of quantum dot cellular automata technological platform altogether. Now, basic features of QCA model. The computation is considered to come both by parallel operation of multiple computing devices or cells. So structurally, when it comes to the question of QCA, it has so many cells. So at the atomic level, there are cells which will be required, or basic building block, I should say, for any QCA architecture. Now, different cells, which are otherwise known as QCA cells, these cells in specific alignment will give rise to different type of circuits. Along with it, certain operations, which we are going to discuss in brief shortly. The quantum level cell size in nanometer range, basically. So, basically, it captures one of the major component of nanotechnology or nanoscience, we call it, to make it efficient to high density implementation. So naturally, if the dimension wise it is in nanoscale level, then in a very small area, high density circuit realization is possible. The state space of cells and the operations performed on them should be motivated by principles of quantum mechanics. So the basic principle which is adhered to in this context is principle of quantum mechanics. In fact, let us proceed. We shall see how they work. Quantum dot cellular automata also interchangeably is termed as quantum cellular automata. So whether it is quantum dot cellular automata or quantum cellular automata, these two are used synonymously. Now comes the question, basic terminologies, building blocks, as I was pointing to, is the cell vis-a-vis called quantum dots, basically. So, which basically there are certain cells or quantum dots, particularly capable to accommodate an electron. A typical cell, a typical quantum dot can accommodate an electron in its place or may not. So when it comes to the question of a cell is basically consisting of a number of quantum dots and so-called channels connecting or having connection between quantum dots, so that through this channel electron can flow from one quantum dot to another. So it's like, suppose two quantum dots or holes are there, holes, and there are two quantum dots and one electron. Let's think notionally. So two quantum dots are there and one electron is there, and there is a channel connection between the two quantum dots. As a result, what may happen is that the electron can take position in either of the quantum dots. Suppose it is residing in a specific quantum dot at a particular point of time, and if the situation demands, it might traverse and move to the other quantum dot through the channel joining these two quantum dots. So that is what I was trying to indicate. So there are possible quantum dots with possible interconnections between them through channels through which electrons can flow and take shelter from one quantum dot to another. And all these together, these quantum dots, the channel, possible electron positions, and apart from them, that there is a so-called regulating mechanism in the channel in the form of a capacitor. So all these together gives rise to what is known as a cell. So these are the individual cell components, and typically cell is structurally an entity like this. And I mean, formation of a circuit is basically alignment of different cells complying or adhering to the principle of quantum mechanics. That is what it is. Now, materially, what are quantum dots? The nanostructure semiconductor dots, basically. Semiconductor. And the purpose is that it contains information in the form of electron position. So, depending upon which particular quantum dot position an electron is occupying, basically some information content is obtained out of it. So the information is realizable from a particular cell structure or a combination of cell structures, where depending upon the physical position or physical occupancy of an electron or a number of electrons in different cells. So how the electrons are aligned in different cells, I mean different quantum dots in a cell, gives rise to different type of information, and This is what exactly or how exactly a quantum dot behaves and used in the context of um, digital information and all. In this context, now it comes to the question of finite multiple number of cells and their alignment. Now free cells align according to the neighbor cells. So very soon we shall see that there is a question of induction, because when two cells are residing side by side, the position of electron in a particular cell will influence the position of the electrons in its adjacent cell. It's effect of induction that cannot be avoided. This is because of Coulombic repulsion, principle of repulsion. So it means that when it is a free single cell, it's nice. But whenever it comes to the question of alignment of multiple number of cells as neighbors, all the cells cannot behave independently or independent of one another. There will be the effect of induction. And accordingly, cells will behave in a specific manner. Now, the other way around, with all these principles being there, now it becomes the challenge to align different cells in such a way that realization of a particular circuit characteristic is achieved. That is what exactly is tried by using this type of quantum dot cellular automata technology. Another extremely important component is the use of clock signal primarily for the energization of cells. Now, from the basic principles of digital circuit or CMOS technology, we know in circuits there is presence of clocks, and clocks are used for regulating or controlling the flow of current from one place to another. Now, in classical framework, this is nice. In classical CMOS framework. But when it comes to the question of usage of clock in this present scenario, that means in QCA, the role of clock is not regulating the flow of electron alone or flow of current alone. Apart from that, clock has got a very formidable role to play in the present context of QCA design, where clock signal not only energizes cells, clock signal not only regulates cells, but it takes the responsibility of energize the cells also. So what is the source of energy of different cells? What is the source of energy of different cells in this particular type of architecture? It is clock. So quite understandable. It means clocks have got two roles to play together in this scenario, in the new scenario. Control or regulation of flow of electrons, number one, and energization of cells also, number two. So source of cell energy is clock. So with these twin responsibilities, clock signals work in the present context. Now the circuits are designed accordingly. Cell-to-cell interaction done by Coulombic repulsion principle. So, as I pointed out a few moments back, and because of this, the question of physical internal wearing, as is available in our classical scenarios, is not there. So, need of internal wearing is not needed, or no need of internal wearing as such in case of QCA technology framework. depicts binary information through electron alignment within cells. So that specific alignment of different quantum dots and the position of electrons within those quantum dots uh, within a cell, this gives rise to some binary information. And how these binary informations are decoded from different alignment of cells, let us observe that now. It has got two variants we have already pointed out outset. There are 4.2 electron QCSL and another is 2.1 electron QCSL. 4.2 electron QCSL is more popular and well explored field already. 2.1 electron QCSL is otherwise comparatively newer and the late generation realization or understanding. So today we are going to discuss about 2.1 electron QCSL only. But for this, the basic, the cellular structure of 4.2 electron or associated things must be understood clearly. Now, when it is a 4.2 electron QCSL, it means that it is a square type of cell, geometrically, from geometric notion, better to say, we can perceive that it is a square shaped cell where there are four quantum dots at the four corners of the cell, and there are possible interconnections of channels, as has already been indicated. And since it is a 4.2 electron, there are two electrons which are going to occupy their places in that four dots or four quantum dots, also known as holes. So there are four holes at the four corners of a square. Geometrically speaking, let us try to perceive it geometrically. And we have to fix two positions out of these four to be occupied by two electrons. In how many ways this can be done? Theoretically, 4C2 ways. Okay. So there are 4C2, that means 6 many options or alternatives. Question is, out of these 6 possible alignments, are all valid alignments? Answer is no. Out of these 6, only 2 alignments are admissible. Rest 4 are not. Which 2 are admissible? Those 2 where the electrons are occupying the diagonal positions of the holes. Since there are 2 possible diagonals in a structure like this, square structure like this, so there are two admissible positions acceptable. Rest 4 are not valid. Question is, why this is so? This is because of Coulomb repulsion, as was indicated earlier. Coulomb repulsion says that two like charges or charged particles, they are going to occupy their positions as far as possible from one another. So if that is so, out of these 4 positions of these 4 dots, which are the 2 combinations that those maintain the maximum distance, the 2 diagonals. So because of this, only these 2 diagonal positions are to be occupied by 2 electrons. So 4.2 electron QCSL, a cellular structure looks like this. Okay. And because of these 2 possibilities, that means possibilities of 2 possible diagonal positions occupied by the electrons, pair of electrons, there will be 2 possible quantum, and 2 possible information. One of these particular alignment will be treated as 0, the other will be treated as one. So information wise, depending upon which type of diagonal positions a pair of electrons are occupying in a 4.2 electron cell structure or cellular structure, there will be a 0 or 1 information wise that we can decode. Okay. Now when it comes to the question of 2.1 electron, it is indicating itself that it has got a structure, cellular structure, where 2 dots are permitted, and 1 electron. Okay. So here the shape is no more a square one, it becomes a rectangular one like this. So it's a 2.1 electron QCS cell, it's a rectangular structure, really rectangular like this. So try to, things are quite understood. There are 2 quantum dots at the end of that rectangle. Okay. And out of these 2 quantum dots, an electron can occupy any of the either of the 2. So here in this particular scenario, the electron is occupying the lower quantum dot position, but it may occupy the other one also. It means that given 2 positions, 2 quantum dot positions, and 1 electron, there are 2C1 many combinations in which an electron can occupy a dot in the possible 2 options. 2C1 means 2. There are exactly 2 options that you can have. Like 4.2 electron QC, where there are 6 possibilities, out of which 2 were admissible, rest 4 were invalid. In this 2.1 electron QC mechanism, both are acceptable or admissible formation, and there is no inadmissible or invalid occupancy like this. Okay, well, then there is a tunnel connecting the 2 quantum dots through which the electron can move from one end to the other, and there is a possible so-called regulated infringement in between in the form of a capacitor, because you need to regulate the flow of an electron as per the requirement. So this is the structure of a 2.1 electron nucleus cell. Coming to the clocking mechanism, which needs some discussion, because clocking, as has already been indicated, happens to be one of the very, very, very important and significant component insofar as realization of quantum dot cellular automata architectures are concerned. So here the clocking mechanism is different from conventional CMOS clocking. Different clocking mechanisms exist in QC domain also. Some of the literatures are available which throw some light on this. However, so far as the clocking in 2.1 electron QC is concerned, functionally it is very much similar to what is used in case of 4.2 electron QC clock. So clock characteristic is very much similar. Provides data flow direction as well as energy supply. Now, achieved with the help of potential barrier. Now here is what is important. Potential barrier means, please note the presence of this capacitor in between the 2 cells on the channel. Now regulation is necessary. Just a moment. Now, the question is, just try to think, let us think in this way. one at the electron, a single electron is occupying one dot position. Question is, suppose it is energized. The moment it gets energized, question comes: should it move to the other dot? Should it move to occupy the other dot or other position? No. There should be some regulation mechanism for that, which means that if an electron is energized, it cannot flee straightway. It can flee or it can move only after attaining or after being energized to a considerable extent. Only then it can move, otherwise it cannot. It's as if I am occupying a room, or say I am occupying a chair in a ground. Now I am sitting there, so scorching sun is there. I am feeling hot. I still shall sit for some time. Physically, I am energized to sunshine hitting, but after some time, it becomes intolerable, and I want to move away from that particular place. That means I am reaching that level of energy. I have become energized to that extent where it is no more possible for me to stay back at that position. So that position is called potential barrier. And this potential barrier is regulated by the capacitor residing there. So the role of the capacitor in the channel in a QCA cell is to ensure potential barrier as may be required. Because of the presence of this capacitor, regulating the flow of electron and ensuring the potential barrier characteristic for its flow, what happens is that the electrons cannot move freely. Electrons can move only after adequately energized from one cell position to other, which means that in order to move from one cell to another, an electron needs adequate or sufficient energy to overcome the potential barrier for that purpose. Otherwise, it cannot move. Understood. Now, QCA clocking is basically of two types. Now it comes to the question of the clocking characteristic. One is Launder clocking, the other is Bennett clocking. We shall discuss them, both of these, within a short while. So they require specific elaboration because in different contexts they are useful, and in which context which one is useful shall we discuss them. When it comes to the question of clocking, both of them, whether it is Launder clocking or Bennett clocking, both of them consist of four phases: switch, hold, release, and relax. So these are different phases associated to any clock mechanism in QCA that is applied. Switch, hold, release, and supply. Now, let us explain them to figures. So let us concentrate on the figure left-hand side. So there are four states, or four phases. And the figure is indicative of the four phases. One is switch, which is basically elevation phase. Hold, it means position retained. The up position is retained for some time. Then release, it means it's downward slope, and then relax. Once again, the bottom position is retained. Now, let us explain how these four phases in a particular clock come into being. So when it is a question, when a particular, energization takes place, okay, it is the switch phase. Because of this energization, the switch phase is what it is indicating upward flow or upward going. Then after energization, the hold phase, that means what happens physically happens in case of an electron. In case of an electron, an electron is presently residing a particular quantum cell. Now energization starts. Just a moment. Energization starts. So what happens is that through the process of energization, then comes the question. First of all, after the process of energization, that level of energization comes when it moves from one cell to the other. It does so, and then the energy already acquired is released, and then the electron starts residing in that new position of the quantum cell. That means the new quantum cell. Quantum dot, I'm sorry. So it's the shift from or switching from one quantum dot to another quantum dot. In order to realize this movement, there are these four phases, one after taking place, one after another: switch, hold, release, and relax. After this, once again, switch, hold, release, and relax. So it is basically these four particular phases will generate one specific period. Okay. So the effect will be periodic with these four phases in a particular clock. Now, depending upon when these different phases take place, which hold, release, and relax, when these operations take place, there may be four possible alternatives, as shown in the figure in different colors, which are known as clock zones. So there are four clock zones indicated by clock zone 0, clock zone 1, clock zone 2, and clock zone 3. So the entire time interval, if it is t, then phase-wise, if it is entire 2 pi, if it is 2 pi, then this 2 pi is subdivided into four components, equal components, with pi by 2 phase lag each. And this, for every pi by 2 phase lag, there will be the corresponding clock phase, and all the phase lags together, all the four phase lags together, one after another, there will be one period complete, one period of 2 pi phase will be complete. And depending upon the position, there may be different clock zones, four possible clock zones, in which is four combinations of switch, hold, release, and relax, they may take place. So they are shown in different colors, and these are different clock zones. Now, next comes the question of there are two types of clocking we pointed out. One is Launder clocking. The most widely used clocking mechanism is Launder clocking. In fact, most of the literature, QC literature, is very much encumbered with use of Launder clocking. It's a very popular one and it's a common one. Non-clocking is an adiabatic clocking mechanism, mostly using irreversible circuit designs. This is important. When the nature of the circuit is irreversible characteristic, we shall touch upon reversible characteristic also maybe in a nutshell later on. But when it's irreversible circuit requirement, design requirement, then the clocking that we use is what is known as London clocking. What is the basic principle of London clocking? Based on years without copy operation. It means that when we move to our next phase, whenever our next phase or next zone is moved into, the question is, here exactly is the importance. The question is whether the previous phase is maintained in memory or not. It means whether the previous phase information is memorized or not. So far as London clocking is concerned, the previous phase or information regarding the previous phase is maintained. It is not maintained. It is erased. That means once a particular clock phase is moved from its previous one, then the information regarding the previous phase from which the movement has taken place is no more there. Since the information of the previous clock phase is not maintained in London clocking, the question of reversibility cannot take place. It means that one step forward movement means you have moved forward and there is no scope whatsoever to move back to your original position or previous position. So this is the principle of London clocking. So London clocking doesn't support or doesn't have any memory support associated, as a result of which the question of reversibility cannot be possible. So from energy point of view, it dissipates energy in each bit of information loss. So the energy dissipation in this context is basically every bit of energy loss, the information loss. So basically energy dissipation and information loss, these two are interchangeable in this present scenario. So far as London clocking is concerned. Now, waveform representation of London clocking is a classical one that we exhibited last time, which is basically London clocking. Now, it is understandable. So for example, if we are in the hold phase, in the previous switch phase, if we want to go back to the previous switch phase, immediately be the previous one, we cannot go back. In order to have the switch phase next, we have to move further in a subsequent, encompassing subsequent clock zones and then move to the next one. So backward movement is not allowed, as has already been. So there is no memory support or supplementation of memory. However, when it comes to the question of reversibility, that is the bottleneck, it's the major challenge area. When it is a reversible, logically reversible scenario, logically reversible means where I should have the opportunity to move forward as well as backward. So the moment I want to ensure that backward movement must be allowed, I need to have the associated memory requirement for supplementing this. And London clocking is going to fail there. So in logically reversible information has to be preserved to achieve reversibility. And this is because of memoryless property of London clocking. It doesn't solve the purpose. You need something else. In fact, for this, Bennett clocking is used. Due to high functional density in recent technologies, energy dissipation has to be optimized. So this is the energy-wise requirement also. So um, uh, when it is come question of clocking, whether it is Lambda clocking or Bennett clocking, this optimization issue is also associated. Now, Bennett clocking came in the year 1973 because of the contribution of Bennett in this context, which is particularly or specifically suitable for logical reversible circuits. It provides minimum energy dissipation. So energy dissipation wise very very advantageous, as you said, based on the concept of copy then erase operation. Earlier in Lambda clocking, copy without erase. Now it is copy then erase. So the question of erase comes only when it is copied, that means memorized. So classically speaking, or simply speaking, Lambda clocking is devoid of any memory support, whereas Bennett clocking is supported with associated memory. Now, it's very interesting. The waveform of Bennett clocking has changed. Earlier, in case of Lambda clocking, the phase lag was uniform. 2 consecutive phases were having pi by 2 phase shift. Now, in case of Bennett clocking, this has become heterogeneous or ununiform, non-uniform. Right? For example, the hold phase is maintained. Try to appreciate the hold phase is maintained longer as per the requirement, because this copy then erase. In order to achieve this, the hold phase has to be maintained longer compared to what is required in case of Lambda clocking, because only by ensuring longer hold phase, you can ensure the reversibility being realized in this scenario. So that is why Bennett clocking is suitable for logically reversible circuit design using QCM. Now, basic components of 2.1 electron QC architectures. There are binary wire, inverter. All these are very much useful, circuit components that must be there in any technology. Digital circuit realization. The binary wire, inverter, fan out, planar coursing, majority voter gate. So let them explain one by one. Going to the binary wire, I indicated that basically the alignment of different cells. So here is exactly what it is. So when it is a realization of binary wire using 2.1 electron QCL, so neighboring cells tend to align according to Coulomb interaction. Look at the figures. So, since the cells are placed or aligned one after another, I should say longitudinally, that way, as the figures indicate, then what are the possible positions of electrons occupying different dots in each and every cell? So please think and get yourself convinced that these are the only 2 possibilities. So 2 type of alignments may be there. When cells are arranged, 2.1 electron cells are arranged in this particular fashion, either what is being demonstrated at the top or the one demonstrated at the bottom. Now, if the upper one, the figure showing at the top, if the particular polarity of a cell is considered as 1, polarity 1 means the left, out of the two, the left side hole is being occupied by the electron. So it means if one polarity 1 cell is ensured, and if the 2.1 electron QCA cells are aligned like this, and at the other end, what you are going to get? A cell with polarity 1 only, nothing else. So polarity 1 cell provided as input will generate polarity 1 cell as output at the other end. Similarly, polarity 0 or input 0, bottom figure I am talking about, will ensure output 0. Is the reverse scenario. So it means that depending upon which polarity is being injected as the input, the same polarity is going to be available at the output end, which is the basic principle of any binary wire. So accordingly, the linear arrangement of cells with neighboring cells tend to align according to Coulomb-Zodiac interaction. When these two issues are clubbed together, so what we get is basically a binary wire realized by using 2.1 electron QCA cells. So in other words, if we want to realize a binary wire using 2.1 electron QCA, what is the, well, basically this type of alignment. Essentially, as we proceed further, we shall see that it is basically more a design issue, circuit design issue, where placement or alignment of cells in suitable manner, that is what is important. Okay, so this is the way a binary wire can be realized. What about inverter? Inverter means the input that it is injected will get the reverse polarity as the output. Now, see, we have got certain rectangular cell structure like this. Now, there are different ways you can align. It's more a sort of placement, specific placement, keeping in view what type of output I want given my input. So there are two possibilities. One is this one. Okay. The topmost figure you just see. Your input is indicated in blue. So if your input, the input characteristic, if you place your cells like this and you put your input like this, the output is getting reversed. So it's an inverter. It means that if I want to have an inverter or achieve an inversion facility like this, so all you need to do is to place your 2.1 electron QCA cells in this way. That's it. Rest is being done by the Coulombic principle and all that. Okay. So another question. If it is allowed that horizontal, instead of horizontal realization of the output, it means like in the same level the inputs are fed, then the top one is your solution. But if it is allowed that, well, they can be orthogonal to one another, then it is simpler. So the bottom figures are going to explain that. So here also you are getting your inverted output, even your input. But the alignment has changed. That means if your input alignment is horizontal, then your output alignment is vertical in the bottom cases. But if you want to ensure the same alignment to be achieved at the output, the one that was there as the input, then the solution is the, top figure. Okay? It depends upon which particular one you need in which context. Coming to fan out. So if it is a single input to be branched like this, as is the functionality of any fan out, that means one to many type of branching. So with alignments remaining the same, that means horizontal alignment. So horizontal input will, one single input of horizontal single input placed horizontally will generate two output in the same alignment. That means horizontal alignment as output. And this is what you get. So the question comes, in order to achieve a fan out, how many cells do you want? That means 1 to 2 output. It means single input to output. How many cells do you want? 1, 2, 3, 4, 5. 5 cells, out of which one is used as the input cell and 2 for the output cell. Okay. Coming to planar crossing. It's pretty interesting. Let us place these 4 2.1 electron QCA cells in this way. What we observe? We observe that the placement of electrons in the holes in different cells will be like this, which indicates that there will be binary wire crossing, somewhat like this. Question is it technically valid one? Can we achieve this? Answer is yes, provided we maintain the flow. We maintain the flow either horizontally or vertically at a time. It means that when vertical flow of electrons are taking place, then we must ensure that no horizontal electron flow or anything like that takes place, and vice versa. So at a specific point of time, either horizontal or vertical must work. When a particular one is working, the other one remains deactivated or inoperative. Next comes the question, is it possible to regulate that? Answer is yes. That is what your clock zone and clock phases are for that. So when you are in a particular clock zone, in horizontal situation, you maintain that your vertical clock zone is in a different one. Since your clock zone, through clock zone, you can maintain the flow of electron in a specific direction, vertical or horizontal, as the case may be. You can always align your cells like this, ensuring that through clock zones or appropriate clocking, I shall use either horizontal alignment or vertical alignment as and when required, giving rise to what is known as planar crossing. This is what you can have. Coming to majority voter gate, in short MV gate, where there are 3 inputs, A, B, and C, and the majority voter gives you the output written like this. In case of 4.2 electron QCA, it is AB plus BC plus CA. That means A and B are, ended. B and C are ended. A and C are ended. Then all these three, they are solved. This means that in case of 4.QC, 4.2 electron QC. But when it comes to the question of 2.1 electron QCA, the third input is inverted automatically. So the majority voter characteristic is AB plus BC dash plus AC dash. This is because alignment is useful or alignment is important in case of 2.1 electron QCA because of its rectangular cell structure, which in case of 4.2 electron QCA, since the cell structure is square, you get no such alignment, no such vertical alignment or horizontal alignment is applicable in that context. So naturally, the majority voter gate characteristic will be different in case of 4.2 electron QCA and 2.1 electron QCA. In case of 4.2 electron QCA, it is AB plus BC plus CA, whereas in case of 2.1 electron QCA, since the third input is inverted automatically, the majority voter output is AB plus BC dash plus AC dash. So that you can achieve using this type of an alignment where the blue marked one are basically your inputs, okay, and non-blue is basically your output. So it indicates that depending upon the majority of the three gates, A, B, and C, the output will be determined. Okay. Now, out of the three, A, B, and C, out of the three inputs, there may be different possibilities. Different possibilities in terms of alignment of inputs vis-a-vis output. So they are indicated with figures, different possibilities in this context. Excuse me. Now the question comes after all these, what advantages do we enjoy over conventional CMOS? It solves interconnection problem, number one. Signal processing is there, we have already seen, among others. Provides ultra high density computing elements, already discussed. Very low power dissipation, so energy dissipation and power dissipation wise is also very advantageous. Ultra fast computing, ultra dense memory storage. So, whether in terms of computing, computing speed, memory storage, energy dissipation, compaction, putting together in a very small area, physical area, interconnectivity, all these positive or issues of advantage enjoyed by QCA over conventional CMOS. Now, how coming to the comparison in respect of advantages enjoyed by 2.1 electron QC over 4.2 electron QC. First of all, less number of electrons involved, naturally, no ambiguous self-configuration. And moreover, majority voter gate in 2.1 electron QC is a universal gate. So the gate universality is ensured because of its automatic invertibility characteristic in case of 2.1 electron QCA, which you may verify if you think, which otherwise is not naturally available in case of majority voter gate version in case of 4.2 electron QC. Now, numerically, determination of the output state. The big bottleneck in case of 2.1 electron QCA or associated research is that no simulator as such is available, no open source or closed source, whatever it may be. So simulator availability of simulator is not there in case of 2.1 electron QCA, which a simulator is available, simulator QCA designer is available for 4.QCA, 4.2 electron QCA. Okay. So naturally, I mean, since in the absence of any simulator, determination of output state becomes difficult. You have to carry out your computation physically every time to justify whatever you obtain. The justification of output state is done using mathematical formulation of Coulomb's principle. So different symbols are explained here. I'm not exactly going into the details of all these things because of shortage of time. I shall try to explain things in a more, sort of superficial manner, not going into the details. It's impossible. A few issues pertaining to reversibility. So reversibility may be of two types, just to get an idea. Maybe of two types. One is logical, another is thermodynamic reversibility. Now, for our purpose, we are basically dealing with logical reversibility, where number of input lines is equal to number of output lines. And definitely logical reversibility reduces energy wastage to a large extent. But if it is asked whether logical reversibility ensures zero wastage, zero energy wastage, answer is no, because there is no physical realization of zero wastage circuit characteristic as yet. This is because it's not possible, even just think of, it's not even possible to, is it possible to have a capacitor which is leak-proof, 100% leak-proof? Answer is no. So in physical sense, it is not possible. But definitely, energy wastage is drastically reduced when we deal with logical reversibility. But however, logical reversibility structurally is more cumbersome. In general, reversibility has one-to-one correspondence between input and output. And the biggest advantage is that flow may be bidirectional. That means from input side to output side, the flow can be obtained as well as in the reverse direction also. That means starting from output side, if we want to move to input side, it is also possible. Okay. When on the other hand, the thermodynamic reversibility, to be specific, deals with the thermodynamic issues associated. In fact, it is beyond our present scope. It's not our cup of tea for the present discussion also. So we just leave it behind. Now, time and again we have seen that energy, low energy, dissipated energy being minimum, energy wastage being minimized, or is reduced as far as possible. So enough of energy, enough of discussion on energy has been taken care of or considered without any formalization. Okay. So when it comes to the question of maybe a few discussions on energy formulations regarding energy, where there are different associated parameters and vis-a-vis their significance. So let's have a quick discussion on that, where there are different notations being used here. Once again, because of shortage of time, it may not be possible to discuss everything. But these are the deciding factors in respect of energy estimation. Now, energy estimation is otherwise it is extremely important in our present context because of the absence of any simulator like this, and we have to you have to determine the energy related expressions. I mean, physically. So there is no way out. Now, for that, for those the different factors which are useful, they are used as different symbols here with their meaning explained in the table. Once again, these are basically derivations which we have done in our work. So these are the associated energy parameters useful in the present context, energy and power parameters. And each and every individual energy parameter has got its different significance, which are enlisted here, which is otherwise useful in respect of technical description of the present context. Well, so once again, we are running short of time. We cannot explain it in more details. I don't think that, everything cannot be discussed for now, but maybe one case study we are going to discuss now for the sake of some understanding, which is a non-reversible circuit design. That means ultimately, and with all the ingredients under consideration discussed so far, how eventually in respect of a physical circuit, circuit can be designed using all these ingredients. And the circuit is definitely non-reversible characteristic. That means it uses Launder clocking as its clocking mechanism, associated clocking mechanism, and it's non-reversible in nature. There are so many. In fact, for the sake of completeness, we shall discuss the flip-flop only, and it won't be time possible to discuss others. So I may please be excused. Let's go to some of the publications. Coming to flip-flop, well, there is SR flip-flop and D flip-flop, which are discussed here or demonstrated here, with the left one being SR flip-flop, the right one being D flip-flop. Now, certain associated issues or interesting points I want to share. So, how many number of cells being used in this SR flip-flop? There are 10 number of cells used. And how many majority voter gate is used? It is 1. So with 10 many cells and 1 majority voter gate combination, an SR flip-flop like this can be designed. Now, I mentioned that it's basically more a design problem rather than anything else. So I want this type of, with this input combination, I want this type of an output. So here your problem is somewhat different. So how optimized way I can achieve that? That means with minimum number of cells, with minimum number of majority voter gate or otherwise, with minimum energy requirement, dissipation wise or requirement wise, minimum energy wastage and all that. So different optimization aspects are there. Keeping all these in mind, how to design or get hold of the best design given a specific circuit character. That is what I want to achieve. So given the fact that an SR flip-flop has to be designed, this is one solution. This is not claimed that it is the only solution. But however, now if it is asked, is it possible to design an SR flip-flop with less than 10 many gates, it becomes a challenging question. We didn't find. So the least one that we could achieve, so far as design of an SR flip-flop is concerned, using 2.1 electron QC is this one. You may try. You're most welcome. Think. When it comes to the question of D flip-flop, which is a derivative of SR flip-flop, as we all know, but since the question of D flip-flop realization from SR flip-flop is done, very interesting. The number of cells goes up. It moves to 12 instead of 10. So 2 additional cells you have to arrange. Question once again, is it possible to achieve D flip-flop using less than 12 number of cells and with maybe one majority voter gate? We didn't find it. You may try, you are welcome. Just a moment. Something I forgot to mention. The uniqueness or one of the strong advantageous side of SR flip-flop design using this type of QCA based architecture is that the SR flip-flops do not suffer from race condition. So SR flip-flop realized or designed using quantum dot cellular automata that do not suffer from race condition. But the typical, bottleneck in case of a CMOS-based circuit realization. Whether it is 2.1 electron QCA or 4.2 electron QCA, SR flip-flop design using QCA architecture, QCA cells in general, they are free from race condition. One very strong point from circuit realization point of view. Coming to JK, this is more comparatively complicated one. The number of cells we require is 23, and majority voter gets used is number is 3. So once again, the question is it possible to design JK flip-flop using lesser number of majority voter gate or lesser number of cells? To us, it is the best that we could achieve. Merging, reducing T flip-flop from JK flip-flop, incidentally, once again, 2 additional cells are required, like the previous, other case, in addition to the 23 one. So, in order to realize your T flip-flop, right? So, this, realizing T flip-flops with lesser number of resources, whether cell-wise or majority voter gate-wise, we could not ensure. So, all are welcome. We may think. Now, coming to the energy analysis aspect of SR flip-flop, the SR flip-flop circuit that we have shown. Is this one, where this one indicates that energy-wise there is an improvement. This is a specific, a particular publication we are talking about. Not important, but in some sense, we may not claim optimized, but it's an open problem. If there is any proposal with even less energy requirement can be done and can be achieved. There is, quantum number wise, quantum number wise comparison, energy analysis of the SR flip-flop that is here. Similar energy analysis of D flip-flop. The proposed one is having or showing the least energy requirement. Further improvement may be thought of if possible. This is the JK scenario. T. So it's now open that even different type of flip-flops that we have discussed. Is it possible to make more energy efficient, to realize more energy efficient designs? Everybody may think this is devoid of race condition, energy-wise very efficient, cell count very much reduced, but it cannot be said or claimed that it is the least one in number of participating cell count. Area utilization wise very good. It means high density or compaction. I think it's time that we should stop because there are so many other discussions, but time is not permitted. So I think this is the point where we may stop. Thank you for your patient hearing. So any question? Any question from the audience, please?
Participants, if you have any question, you may ask. Are there any questions?
Thank you. I think now it is lunchtime for all.
Sir, am I audible to you?
People must be hungry. Yes. Yes.
Sir, thank you very much for.
Yes. Let me stop sharing this.
And you have shown us.
Yes, please.
Have shown us the alternate which might be in this valuable session.